Okay, here we go. Miscellaneous timers. So we've done the weekly timer, we've done the yearly timer. One thing that we remember about the weekly and yearly timer is they only have user parameters. Okay, we do not actually input into the weekly or yearly timer. All we do is compare the real-time clock inside the logo, the integrated clock, with the time plugged into that weekly or yearly timer, and we turn the bit on or off. Now we're going to talk about the miscellaneous timers that we call. There's about 4 or 5 miscellaneous timers that do use an input. As an example, let's say I have a timer that, or a motor that I want to turn on 5 seconds after this input, okay? Or I want it to stay on for 5 seconds after this input's taken away. Things like on delays, off delays, pulse timers, on-off delay timers, retentive timers. We're going to talk about all of those. The first one we're going to talk about is the on-delay timer. Okay? The on-delay timer has 2 pins on it. Let me draw one up here. Let me move it over just a little bit. Okay? It has 2 pins on it. The first pin is my enable pin. And that's a black pin. The second pin is a green pin. What did we say about green pins?
User parameters.
Those are the user parameters. So this is a time in seconds, minutes, or hours. This is my on delay. My on delay parameter. One other thing about this timer is that the way we identified our weekly and yearly timers was by kind of looking at the middle. The yearly timer had MMDD inside of it, which meant month and day. Makes sense, that's the date of the year. The weekly timer had a picture of a clock, so we knew it sensed time, right? And that's another way that we could identify a timer. The on-delay timer is a little different. It's got some pictures of some square waves. Okay? This actually makes sense too. Okay, and I'll explain to you why in a second here. All right? As you look at this, I have my enable, I have my on-delay parameter. I might change this on-delay parameter. You can leave it in your notes that way, but I might add a little bit there. I might call that time, T, and maybe I make it 5 seconds. Okay? Then what you're looking at when you look at these square waves is this. That's your on-delay time T. That's your 5-second delay right there. So let's take a look here real quick. The enable is this square wave up here. When the enable makes a 0 to 1 transition, when it goes high, from 0 to 1, I start timing. That's what the dotted line signifies. Okay? Once I've timed out past my parameter, which could be 5 seconds, 5 minutes, could be 5 hours. Once I've timed out past that, then my output's going to go high. So this waveform represents my enable. This waveform represents my output. Okay, and it just shows 2 states, 0 or 1. Does that kind of make sense to you guys? The enable goes high, makes the 0 to 1 transition. That could be a switch, right? It could be a limit switch. Could be anything. Could be your M1 coil. When that M1 contact goes high, 0 to 1, when I hit start, that goes high, that starts my timer. When the time is elapsed, my output is going to go from 0 to 1. It's going to go high. When does my output go back to low? 1 to 0, right here. But what's occurring on the enable at the same time?
Shutting off.
Yeah. When this goes 1 to 0, that goes 1 to 0. So The OnDelay timer starts timing when the enable goes high. When the time expires, the output goes high. When the enable goes low, what does the output do? Goes low. So we could write that in words. The OnDelay timer starts timing Another way of saying when the enable goes high is to say when the enable is true. OnDelay starts timing when enable is true. The output turns on, or the output is true after t seconds, okay? Or it could be t minutes or t hours or whatever. And remember that t seconds, I'm underlining it in blue. Why am I underlining it in blue? That's a user parameter, t seconds, okay? Then the output goes low or you could also write output turns off, same thing, or output is false. I'm going to write turns off because we were using turns on. Output turns off when? When does that happen? When the enable is what?
0.
When the enable is low. Perfect. The output turns off when the enable is false. We use the word true up here. We use the word false down here. So the OnDelay timer starts timing when the enable is true. The output turns on after t seconds, which is a user parameter. The output will turn off when the enable is false. So after t seconds, if that enable stays true forever, what does the T001 bit do? Yeah, it stays on forever, right? This T001 contact would stay on until that enable went back to low. Does that make sense? All right. We'll slide across the board for a second here. We're going to do the retentive OnDelay timer. Okay, first of all, what does it mean to retain?
Hold.
To hold, yeah, exactly right. Retentivity, if I had to define what retentivity was, if I had to spell retentivity, I think I got it. Retentivity is maintaining I'm defining retentivity as the PLC sees it. Retentivity would be maintaining the current value even when the enable is lost. So even if I lose the enable, it's going to remember how many seconds have elapsed. The OnDelay timer, what did it do when the enable was lost?
Turned off.
It turned off. The retentive OnDelay timer is going to maintain the current value even when the enable is lost. Okay? Let's talk about the pins on the retentive OnDelay timer. I'm going to label this as T002 just because our first one was T001. Okay? There's more pins on the retentive OnDelay timer. And I might have to peek at it real quick here. Bottom's green, I got that. Okay, here we go. If we know that the green pin is a user parameter, we know that all the black pins are going to require something to be physically hooked up to them, right? So the first pin you're going to see is the enable pin. I just didn't want to, I had to peek at LogoSoft real quick because I sometimes will flip-flop these. I didn't want to do that today. The first pin is our enable pin, okay? The second pin is our reset pin, and the third pin is blue. And what did we say about blue pins? Or green pins in that matter?
User parameters.
That's our user parameter. And so again, this could be a time t. Maybe this time I set it to 10 seconds. Could be 10 minutes, could be 10 hours. Okay, could be anything I want it to be. The square wave that's internal, this is where these square waves become important. And I think you understood it in the OnDelay. That we went high, we started timing. When we went low, we turned the output bit off. This guy's going to look a little bit different. We're going to see the enable again. The enable's always, your enable waveform is always the waveform that's on top. So we're going to see our enable go high, and then we're going to make our enable go low right away. Okay? And then our output waveform is going to look like that. And we're going to show this right here. Think back to the definition of retentivity. Maintaining the current value even when the enable is lost. So what does that mean? That means that this pulse on the enable pin could be momentary. It doesn't have to be held anymore. Okay? So as soon as that pulse is felt, the timer is going to start timing. I don't care if that pulse is that wide in duration. I don't care if the pulse is this wide in duration. It just has to be pulsed. And once it is pulsed, that timer is going to start timing. And once the time has elapsed, once the time is greater than time t, the output's going to do what? It's going to turn on, right? Go high. Notice one thing about this timer. What's one physical difference about the pin configuration of this timer?
It's got a reset.
It's got a reset. So here's the deal. On the OnDelay timer, the timer would reset anytime the enable is lost. If this is true, if the enable can go high and go right back to low, and then the timer turns on, if I didn't have that reset pin, how would I reset this timer? You wouldn't. That's exactly right. It would stay set forever. Okay? Anytime that PLC was on, once I pulsed it once, it'd be a one-time use timer and it'd be on forever. Because of this fact, we are required to have a reset pin. Okay? So if we had to define how the retentive OnDelay timer works. The retentive OnDelay timer starts timing when the enable is true. That part of it is the exact same thing as the OnDelay timer. That's why one of them's an OnDelay and the other one's an OnDelay. This one just has a retentive piece to it. So it starts timing when the enable is true. Now what could I add to this definition that would describe the rest of it? What else can we write about the retentive OnDelay? We need to add something to this, right?
Once the timer times out, it stays on.
Yes. Not necessarily once the timer times out. It will continue.
Oops.
It will continue timing regardless of the enable signal. It's going to continue timing even if the enable signal goes back to low now. The enable signal had to go high for it to start timing. Okay? So it starts timing when the enable is true. But at this point, the enable can go false, and it will continue timing. So then we can say after, and what does blue mean? User parameter. After t seconds, the output turns on. And we need to add one more thing. What does the reset pin allow us to do?
Reset it.
To reset it. The only way to reset the output is with the reset pin. Okay? So in this case, the only way we're ever going to turn this timer off is with the reset pin. So it's a little bit different than the OnDelay timer in that it retains where it's at. It remembers. It maintains. Okay, that's what retentivity means. That is definitely a question you guys are going to see probably on every test you take in this class. We're going to ask you, what is the difference between a retentive and a regular timer? What does it mean to be retentive? What does it mean to retain? Okay. One option, the OnDelay timer works great with a switch. Because when I turn the switch on, the switch stays on. This one might work better with the push button. If I just needed to start push button to pulse the enable and then get it going. Question back there.
With the reset pin, does that mean that a voltage is applied to it, or?
Just means an input. So the reset pin, I might have I1 enables the timer, and I2 resets the timer. And maybe this is my start push button, and maybe this is my reset push button. Does that make sense? Yep. Yeah, don't think voltage, because the PLC, the program,
Right.
it doesn't know voltage. All the PLC knows is contacts and coils and boxes. So, any other questions on retentive timers? And really, only the OnDelay side do we work with a retentive timer. Okay. All right, I'm gonna start erasing over here first. And I'll leave that up there for a second for those of you that might still be writing. The next timer that we're going to work with, if we can delay turning something on, what else might we be able to do? Delay turning something off, exactly right. So the next timer we're going to work with is the OffDelay timer. Okay? And again, these functional blocks, those square waves that are internal to those functional blocks actually do make sense. Okay? And I'm going to have to cheat again. I don't always remember my pinout. Oh, come on now. Yep, reset's always the second one, apparently. Alright, so the OffDelay timer, we'll call this guy T003. Just from this picture, what do you know about the OffDelay timer? 3 pins. Two of them are physical inputs. One of them is a user parameter. So let's go ahead and put this guy in as 7.5 second user parameter. And the upper pin will be my enable. Second pin will be my reset, just like it was in my, my retentive OnDelay timer. And now let's draw the square wave. There's my enable. My enable goes high for a brief pulse. Okay? As soon as the enable goes high, the OffDelay timer is going to turn on instantly. So the T003 bit turns on as soon as the enable is on. Enable goes on, T003 bit turns on. Okay? So as soon as the enable is true, this contact is true. Make sense? The difference is when it turns off. Right here. This is the trigger for my OffDelay timer. What is the trigger?
Is that when it starts timing?
That's when it starts timing. And what is the trigger on the enable?
When it's false?
1 to 0 when it goes false. When the enable goes false, my timer is going to start timing. Now if this was time t, 7.5 seconds, this is time t right here, 7.5 seconds. So the output remains on for time t. Does that make sense? Does the square wave kind of get the, you should be able to, at some point, these square waves should start making sense to you, and I should be able to pop anyone up there, and you'd be able to say, oh, that's obviously an OffDelay timer because the output stays on after the input goes off. Right? All right, next. Let's go ahead and define it a little bit. The OffDelay timer. The OffDelay timer bit turns on whenever, anytime, whenever the enable is true, so the OffDelay timer's bit, I could put timer's bit, that bit, that T003 bit in this case, will be on whenever the enable is true. Okay? The bit stays on for, and again I'm going to do this in blue. Why am I doing this in blue?
User parameter.
That's my user parameter. For t seconds after the enable does what?
Goes false.
Goes false. Absolutely. So the OffDelay timer bit goes on instantly when the enable goes true. But the OffDelay timer keeps the output on for t seconds after the enable goes false. All right? And we'll at least use an on and OffDelay timer in our little example we'll do here in about 5 minutes.
So the power is on. As soon as the enable's on, the power's on. And then as soon as the power's off, that's when the timer starts to kick.
That's when the timer starts timing. Exactly right. Yep. All right. Another one.
Could you have a timer for the enable?
Oh, absolutely. Yeah. You can daisy chain. There's no reason why this enable couldn't be a timer bit. T001 is going to enable my OffDelay timer. Sure. Absolutely. Yep.
Are these timers, are they physical devices or are they also internal to the...
They are only internal to the PLC. Good question. Are they physical devices? No. The only physical devices I have with this PLC are what?
PLC.
Yeah, the PLC screw terminals, right?
Right.
L1 neutral, I1, 2, 3, 4, 5, 6, 7, 8. and Q1, Q2, Q3, and Q4. I also have the push buttons, the cursor keys. We looked at that last time. We can use those as physical inputs. And I also have a physical output in that little LCD display screen. Okay, and I know we haven't talked about that much yet, but that little LCD display screen is actually a special function where I can display messages on that screen. All right. The next one. Guess what this one does? Yeah, it combines the functions of both, right? Okay. Let me draw it up here. We'll call this one T004. I'm going to slide it over just a little bit so I stay in the camera best I can here. Again, if I draw just two pins on this, one of them black and one of them green, what do you know about these two pins? One of them is?
Enable.
One of them's an enable and one of them's user parameter. Exactly right. So this is my enable. And now this user parameter is a little different. It's going to have two parameters. Why do you suppose it has two parameters?
One off and one on?
Yeah, one on, one off. 5-second on delay, 10-second off delay. Okay? And you'll actually see that when you open these up, you'll see one of them's on, one of them's off. Okay? Now if we had to draw a square wave for this guy, what do you suppose the square wave would look like?
A cross between the on and off.
Exactly right. A cross between the on and off delay. So the enable, I might make this one a little bigger so you can see it here. The enable is going to go high, and then it's going to go low. Okay? The on delay portion is going to start timing right here, and then it's going to turn on. So this would be one of my parameters right here. Okay? These are dotted lines. So this would be my on delay, which would be, maybe I would call that T1. All right? And then I'm going to come over here. So I'd make my timer a little bigger to show everything. But then I also have another dotted line. And what does this dotted line represent?
Off.
My off delay. And this would be time T2. Okay? And I'm not going to say much more than the on-off delay timer . You guys know how these work now, right? I mean, we know how the on delay works. We figured out how the off delay works. We know that the on-off delay timer just takes both features and puts them in one box. Okay? And can you see that from the diagram? Does the diagram make sense? I have two delays now instead of having one. The square waves are just offset to each other now. All right? Yeah.
And one starts in and one starts outside of the wave. Would that tell you which one was on and which one was off?
One more time.
With the scattered lines there, you got one inside the wave and one outside the wave.
Yep.
That would tell you which was on and which was off.
You got it. Yeah, this would be the on delay portion timing out, right? And this would be the off delay portion timing out. Exactly right. Yep. Because again, this is a time T. This is T2, and this would be T1. Okay. So there's two time delays there that we're looking at. Very good. Very good. All right. Any questions on the on-off delay? Now here's the question. I sometimes get this question. Well, what if I want to use the on-off delay as just an on delay?
Then you don't put the off.
What's that?
You don't set the off.
Or I set the off, but what do I set it to?
0.
0.
Okay.
Yeah. Or what if I want to use the on-off delay as just an off delay? I would set the
On 0.
the on to 0. But I always tell people don't do that. The reason why is, yes, this can do all the functions you need, and by setting 1 to 0, you've created an on-delay timer. If the off delay is 0, this essentially is just an on-delay timer, right? But the problem you run into there is this guy actually eats up a little bit more memory than just an on-delay timer by itself, because he's incorporating both functions into one timer. Okay? So if I can put, let's say, 83 timers into my program, 83 on-delay timers, I might only be able to put 60 of these in there because of the program memory limitations. So it doesn't, and really in this class, for the for the purposes of the logo in general, you don't typically run out of memory on the logo. Because the logo only has 8 inputs and 4 outputs, and it's very limited, we don't typically write programs to control the whole Ford Motor Company assembly line using one single logo. And that's a little bit outrageous, right? What we do is, and even for that matter, if I have a whole assembly line, I don't even use one PLC. I might have one master PLC that's sending signals out to other PLCs to start a process. And it's broken up into processes. Here's a process where I'm stamping parts out of sheet metal. Here's a process where I'm shooting welds in a frame. Here's a process where, wheels are being put onto the body. Each thing is a process that might require its own machine and its own PLC. And maybe I have one master control that's sending signals as kind of the road cop there, or the traffic cop. He's kind of just sending signals to keep the flow moving, to keep everything working together. So, all right. Yeah, I'd be very surprised in this class anyways if you ever run out of memory on the logo, because it's got a lot of capabilities for its size. Alright. Now we are almost done. The asynchronous pulse timer. Asynchronous pulse timer. Okay. The description of it, or the physical on it. Let me grab one, make sure I get the context right. Okay. This is what it looks like. Again, what do we know about this timer? What does it have?
Enable, reset, user.
Yeah, it has 2 pins, 2 inputs, right? And it has a user parameter. It does have an enable pin, you are correct. But it no longer has a reset pin. Now it has what's called an invert pin. And then the user parameter has 2 time values to it. And they are called pulse width and inner pulse width. One is pulse width, one is inner pulse width. So maybe I have 0.5 seconds, 0.5 seconds. So it's on for 0.5 seconds, it's off for 0.5 seconds. This would be equivalent to saying 1 pulse per second. Okay? And the way they draw the picture on this one, it's kind of strange, but it does make sense. They only show one waveform. All they're doing is they're showing a pulse. And by making them different sizes, what are they showing? They're showing that you can vary these, right? They're saying I could have the pulse width be 1 second and the inner pulse width be 1/4 of a second. I could have the pulse width be 5 minutes and the inner pulse width be 1 minute. Okay? What does this guy do? This is a lot of times you'll hear us refer to this as our flasher bit. Okay? So you've got that nice little radio tower. You're working for, I don't know, Care 11, the local news company or the local radio company, and that radio tower looks something like this, right? What do they always have at the top of that radio tower? The blinking light right up here, right? Okay? And so your boss says, well, you know, we need to put a light on this radio tower, but I want some sort of industrial control that's durable, that I can change the rate at which that flashes if I want to at some point. Well, it'd be real easy to take a logo and wire it up there, right? And hook up a T005 contact to one of the outputs, Q1, and set up that logo to pulse at half second on, half second off. And what is that light going to do now? Half second on, half second off. And it'll flash at any rate I want it to. Maybe FCC is going to change their rules. Maybe instead of 1 pulse per second, they're going to make it 2 pulses per second. Because some guy in an airplane crashed into a tower and, you know, he looked at it for a split second, didn't see the light, and ran right into it. So the FCC decides to change it. How hard is it to change the rate at which this flashes?
Not hard at all.
Not hard at all. If I did this with a 555 timer like you guys did in second quarter, and I put it on a circuit card, and I wired up a relay to it, how hard is it to change that? A little bit more difficult. Might require rewiring. Might have to change one of those resistors out. It was like RA, RB, and C1 were your main components when you wanted to create an asynchronous timer. Well, I'd have to actually physically change something out. If I thought about it ahead of time, maybe I'd put a potentiometer in there. But even then, with the potentiometer, I was limited on my duty cycle. I could only get down to 50%. Then I had to add in a diode. There was all kinds of special things you had to do to make it flash at different rates. To make this flash at a different rate, I hooked my computer up to it. I changed these two numbers. So now instead of half second on, half second off, I do 0.25 seconds on, 0.25 seconds off. And now instead of 1 pulse per second, now it's 2 pulses per second. Pulse width. Pulse width is the high time. The inner pulse width is the low time. Pulse width is the amount of time that it's on. The inner pulse width is the amount of time that it's off. Pretty simple, right? All right. Moving on. We got one little part left. And then I think we'll do a quick demo and we'll be done. Applications. These are timer applications now. You guys need to come up with 6 before we can move on to the example. Give me 6, maybe just kind of go around the room. Give me 6 applications where we might use a timer.
A grocery store door.
Grocery store door, nice.
Motion light.
Grocery store door. So, what do you mean on grocery store door? Explain.
Well, like, you want it to open up, but you don't want it to stay open. You want it to close after.
So maybe I walk up and that sensor senses I'm there, the door opens up and it stays open for 5 seconds or something like that, right? And what was the next one?
Motion lights.
Motion lights, I like it. Explain, what's a motion light?
When you walk past it, it turns on, stays on for a preset period of time.
Yep. Walk past it, it's going to stay on and it stays on for a set amount of time. How about some other ones?
Heating or cooling, like AC.
Heating or cooling, very good. This could be applicable to kind of like we did with our sprinkler system. Let's say in your bathroom, underneath your ceramic tile floor, you have some radiant warm water that gets routed through there in the wintertime, right? What does that do for your floor?
Keeps it warm.
Keeps it warm. But using a weekly or yearly timer, I could determine when it stays warm and when it doesn't stay warm, right? No need to run that stuff when it's 95 degrees outside. All right, or if I'm in Arizona, maybe I have an analog input to the PLC that actually reads temperature. And you get really good, you'll actually feed analog signals back to the PLC that'll read the actual temperature so that I can turn things on or off. We need 3 more.
Like a garage door that opens up when you drive in front of it, stays open, and it shuts after you drive through.
Sure. So maybe a garage door timer. Okay. Maybe we actually had a gentleman come through here on a tour the other day, and he was a manager for an automotive place. And the problem they had was a carbon monoxide system because they needed a fan to stay on for so long when the garage door was shut or open, I can't remember exactly, but they're constantly pulling cars in and out. So maybe it's a combination of the garage door staying open for so long with the fan staying on for so long to make sure that we exhaust all the fumes out of the building or something like that. Sure, absolutely. How about a couple more? That's it, there's only 4 of them.
Alarm system.
Alarm system. Okay, here's a great example. Let's say on your alarm system you arm your alarm, right? When you arm your alarm, how long do you have to get out of the house before it actually is going to be,
30 seconds.
yeah, maybe 30 seconds, maybe 45 seconds, maybe that's the value I can trigger, or I can program, right? Maybe the strobes or the sirens or something for the alarm. Maybe they're going to, there's your alarm. What kind of timer do I use to create an annoying buzzer that goes, Asynchronous timer, very good. What else?
Conveyor belts.
Conveyor belts, very good. So we got 6. Conveyor belt, we could go back to that asynchronous timer. We could say when I hit start, the annoying buzzer comes on, and then the conveyor belt kicks on. What would that do?
Lets you know what's coming on.
Lets you know what's coming on. If someone's sitting on it, they're hopefully going to jump off of it. Okay. The other thing we could do is maybe when I press a push button, maybe it stays on for a set amount of time, kind of like a jog. But instead of the jog having to be held, now I can hit it, pull some boxes off as they're coming to me, and then 5 seconds or 10 seconds, maybe I have to hit it again. You know what I mean? So it's kind of a jog with a built-in timer or something like that. 6 really good applications that you guys have come up with there. So, all right, now we're going to go into a quick demo. Quick example. All right, let's do a, we're going to do the conveyor belt. I like the conveyor belt example. We're going to do that one.
Should we do it on the PLC program, I think?
Yes, let's, let me real quick, I'll get a stack, they're coming around. Yeah, they're passing out again, for those of you that might be watching the tape. Program listing sheet, best place to start when you're writing a PLC program. Start here. It doesn't have to be perfect, but it gives you a good idea of where you're heading, of what components you need, okay? So the conveyor belt system, I want a 5-second warning with a buzzer that is pulsating 1 pulse per second. That's what 1 PPS means. So when I hit start, I want the buzzer to sound, and then I want the conveyor to turn on. Kind of like where we were just talking about, okay? And I want that buzzer to sound at a rate of 1 pulse per second, which is also equal to 1 hertz.
0.5.
Or 0.5 pulse width. Very good. Very good. So we'll start our program off. Now what I'm going to tell you, starting today, anytime I'm going to use a start and a stop, let's say, it's always a good idea to start out with that, I call it my system run bit, that M1 coil, okay? A lot of times you don't know where you're going to start. I'm going to call I2 my stop. I'm going to call I1 my start. M1 is system run. Okay? All right. Then what do we need when we do that? We're going to use a start and a stop, and this system run bit. Well, the start is only momentary. What do we need? The holding contact. Very good. So then M1, my system run, also becomes my holding contact. Okay, so now I have a way. I have a means to start up a conveyor belt. I have a means to start that pulsating buzzer. Okay? There's my system run bit. Alright, so next, we're going to take that system run bit M1, and we want to start a pulsating buzzer. Okay, and this is where it really helps when you guys do those sheets to do them in pencil. also. Because what you might find, you know, this rung is fine. So if you started it off in pen, this rung is good. We're not going to make any changes to this rung. But what we might find is we may make mistakes. We have to kind of erase and add something here, take it away there, and rework and see what we get. All right, so first of all, I want M1, my system run, to start some sort of timer. And for right now, all I'm thinking about is I need 2 timers. What are the 2 timers I need in this case? An asynchronous is 1. So I'm going to come over here. T001 is my async. Sometimes I try to write it in my box, sometimes I don't. But I'm going to have 0.5 seconds, 0.5 seconds. What does that mean? What does it mean?
1 pulse per second.
Yeah, 1 pulse per second, half second on, half second off. Exactly right. And what other type of timer do you think I need? I want that conveyor belt to start, I want it to turn on 5 seconds after I hit start. OnDelay timer, perfect. And I don't get in the habit of drawing the little square waves in there. Maybe you do. But I'm just going to call it my OnDelay. And I'm going to write my parameter in there. We're going to call this a 5 second. Not a 0.5 second. This one's a 5 second OnDelay timer. All right. So now let's kind of slide over just a little bit. How do I make that buzzer pulsate? Here's my buzzer right here. We'll say Q1. This is my buzzer, or my alarm horn. So I've got a buzzer, I've got an alarm horn. How do I make that buzzer, I'm going to write it above it, just in case I'm a little bit out of the picture there. How do I make that buzzer pulsate?
Put it open in there, that's coming off of T001.
T001. I'm going to start off with M1. Any ideas why I'm starting off with M1?
It has to be close.
Yeah, I never want this thing to sound unless we've hit start, right? So I have M1, and then I have T001. And what is T001 going to allow me to do? And we're pulsating, right? All right, and then I'm just going to connect it up. Maybe I need more stuff in there, I don't know right now. I'm going to clean this up a little bit too so we have more room here. Buzzer, Q1. All right. What we know though is as soon as I get system run here, as soon as we have system run, this timer starts flashing, right? What also is this going to do? It's going to start timing, right? At the same time. When it gets to 5 seconds, its bit is going to turn on. So let's go ahead and turn on that conveyor belt. M1 is my system run. T002 turns on Q2, which is my conveyor. We're done, right? Looks good. Well, let's see. I get start, I get system run. System run starts my async. The async makes the buzzer go 5 seconds after I get system run, the conveyor belt's on. What's the problem right now?
Turn the buzzer off.
Yeah, the buzzer's still going all day long, right? Because there's nothing to kill the buzzer. What are we going to use to take the buzzer away? Let me ask you this. The buzzer is on when the conveyor's not on, right? When is the buzzer ever on when the conveyor's on?
No.
Not supposed to be.
When Q2 is on.
What could I put here?
Q2.
Somebody said it. How about a Q2 break? What's that going to do? When the buzzer turns, or when the conveyor turns on, what's the buzzer going to do? It's going to turn off, right? Does that make sense?
Mm-hmm.
So the buzzer goes, I hit start, I get conveyor kicks on and is running, the buzzer is not on anymore. When I hit stop, what's going to happen?
Whole system shut down.
The whole system shuts down. Does it work? This is the basis for about, I don't know, about half the, maybe about half the jobs you're going to write in here. A lot of jobs we're going to ask you to add a warning alarm to bring the machine on, and maybe something to keep it on at the end, other things. But we used 2 of the timers, so we applied 2 of the timers that we talked about today. Does anybody have any questions? That's it.